Okay, good afternoon. Short class today. Um, so apparently there are a lot of issues with the homework, with the online system. It's maddening to students. It's frustrating for me too. So I have been reviewing all the problems in depth from as much time as I have, but I have more time over the weekend. So the problems that have errors, students go ahead and do your attempts, and I will either I will adjust the points. I don't know exactly how I'm going to do it, but I did it previously where I dropped out, I removed that problem from the homework. So I'll either remove it or make it extra credit or something, but it won't affect student grades. Okay. Yes, I know. Yeah. Yeah. All the time. Yeah. So I apologize about that. Um, I haven't had this issue with some of the earlier chapters, but I don't know. These transistors and MOSFET chapters seem to be more than usual. Yes. Yes. So all the work that you have done, which it does not matter now for your grades, but I just, as a working engineer, this is something that you'll encounter. You'll have circuits, you're trying to troubleshoot, you're trying to figure out, you're trying to design something that's completely unknown, right? So it's a real life scenario all well. But in this case, of course, it's frustrating because we know that the system has a accurate answer. We try to find that answer and it's not recognizing. Okay, so that was about the homework. We'll have one more quiz. Haven't yet decided whether I want to have quiz on Monday or might have it on a Wednesday. Friday, more likely than not, it'll just be an off day. So I usually do like a review on Wednesday, and then Friday is like a study day. Students can just come ask me questions, get any doubts clarified, office hours kind of stuff. And then there are some students who are taking the exam on a Saturday. So you should have plenty of time to do that. I will post the announcement shortly later, not maybe around 8 or 9 o'clock once I get done with sit down to work later tonight. So I'll post an announcement whether the quiz is going to be on Monday, but more likely than not, I'm leaning towards having it on a Wednesday, and it'll be on logic gates, which is the last topic that we have done. Okay. The CPE banquet is tonight. How many of you are going? Just one. That's it. Is it? Wow. It was 45? Cool. That is funny now. It was $50? Seriously? I don't know. The E banquet was like 50, $20 this year, I think. Well, it depends on how many sponsors we can get. So, if you have more sponsors, you can make subsidize it. So the E banquet was like 20, and last year I believe it was like 15, I think. But it was like yeah, I can understand. I thought that tickets were like far cheaper than that. So anyone run into Professor Hummel? Y'all remember him? He's here for the banquet. That's the reason I knew. So if you see him on the hallway, feel free to chat. Okay. All right, transmission gate. One more slide on the transmission gate. So a quick recap: transmission gate consists of a CMOS, a pair of transistors, NMOS and PMOS. Sources are connected together, drains are connected together. You have a control voltage. Both transistors are either on or off at the same time, and whatever input we give is available at the output. So it behaves like a switch. And there are many applications for a transmission gate. If you wish to simulate it, again, with many things in LT-Spice and Spice in general, we can create a circuit. Here is the transmission gate circuit, and here is the inverter circuit to create, the control voltage. In the control voltage, we have VC and VC bar, right? PMOS and NMOS require opposite polarity voltages to turn on. And so here is the inverter circuit for the control voltage. And this is the transmission gate. Okay. So a simple explanation for this was that we are applying input V in, ramping it up from 0 to 5, and then from 5 to 0. And this one is a pulse. It's like a gated pulse that's going into the inverter. Obviously, it should turn on the gates at the same time. So when the pulse arrives, the device is turned on, and whatever we have at the input is available at the output. Absence of pulse turns it off, and then no output. And so this transmission gate can be used as a digital as well as an analog switch. Okay, you can use it as a digital as well as an analog switch. So in the previous slides, we spoke about how this is a bidirectional analog transmission gate, right? Bidirectional because you can apply the input on either side and you can obtain the output on either side of this device. All right, next topic of buffering. So in logic gates, in most circuits, when we talk about buffering, we are talking about isolating the output of one circuit and the input of the following cascading circuit. Okay, so some examples that some incidents just happened recently was some lab groups were trying to turn on there's a solenoid LED motor, and we're not able to drive enough current or enough voltage to turn on our output device, right? So if let's say, for instance, we are trying to turn on an LED. LED would require typically at least 1.1 to 1.2 volts to turn on, and few milliamps of current, about 15, 16 milliamps of current. So if your output device is less than, let's say, 1 volt going into the LED, it's not going to turn on. Or even if you're supplying, let's say, 1.5 volts, but the current is only limited like 1 milliamp or 2 milliamps, again, LED is not going to turn on. Same thing if it's like a solenoid or a motor or any other application, right? So the output of a circuit is not enough to supply either voltage or current to your following circuit or to the output. So in that case, we need to isolate, we need to buffer, or we need to place a buffer between our circuit and our output. In general terms, circuit 1 and circuit 2. So if you have circuit 1, and you have circuit 2, you place sort of a buffer in the middle. What the buffer does is it provides, let's say this is VDD, this is VDD or ground. So the buffer circuit is actually providing the voltage and or the current to your follow-on circuit or the output circuit. And the buffer itself will take the input signal and is going to activate or deactivate the output. So the simplest of isolation buffers was the op-amp in a unity gain mode or a voltage follower mode, where you simply take the output of an op-amp and feed it back into the negative terminal or short the negative terminal with the output, and you provide your input to the non-inverting terminal. Do you remember that by any chance? You had an op-amp output. Oh, sorry, it should be silent. This is the input. This is the output. And you remember this circuit, right? Voltage follower. The reason it's known as the voltage follower is because V out is exactly equal to V in. The point of this circuit is that the power to drive the next circuit comes from the power rails of this op-amp. Okay, the input is simply taking the shape of the waveform and providing it to the output. So this would increase, this circuit increases the driving current and it acts as an isolation buffer. So we call that loading effects, how the load affects the previous output, previous circuit's output. Okay, so in logic gates, again, this is very important because most logic circuits or almost all logic circuits are built up of cascading connections of multiple circuits, multiple gates, right? And so you have these logic gates, and the outputs of these gates are sometimes not enough, well, not sometimes, oftentimes not enough or not sufficient enough to drive a follow-on circuit, right? And so we want to add a buffer or a buffer circuit at the output of these gates. And so we'd add this by adding an inverter, simple inverter, which can be realized with only 2 transistors, right? We don't want to add complexity to the circuit. So the simplest of circuits that we can attach is an inverter. So we attach an inverter, but now your output is inverted. So you attach another inverter. And over several decades, this is kind of like the de facto standard, because this is the cheapest and the easiest way to implement a buffer circuit. Okay, so if you have a standard logic gate created with, let's say, 4 transistors, 6 transistors, the output resistance or the output impedance of this logic gate depends on the input. If the input is, let's say, 0, 1, 1, 0, or 1, 1, the output resistance would be equal to the channel resistance of the transistors, PMOS and NMOS transistors. Okay, but if the state is undetermined, if it's like 0, 0 or 1, 1, for instance, the output resistance could be far lower, higher, or the state would be unpredictable. And if that's the case, we need to add buffer circuits at the output. And so if you add these kind of inverter circuits at the output, if you have 2 inverters back to back, then, or in series, then whatever you feed as input to the first one is the same signal that you obtain at the output of the last one. And the output resistance right here would be as low as possible. Okay, there are some design parameters and specifications that we take a look at. Let's see. Oh, so the point is that it does not depend on the input conditions, right? The input could be anything. The state of the output does not control the output resistance. That's the point of having these kind of buffer circuits. Okay, so we have our standard gates. The smallest gate is the inverter gate, right? If we have an inverter gate and we wish to connect a buffer to the output, or we wish to buffer the output, do not want to connect anything directly to the output terminal, so we have a buffer in there. Well, to create a buffer, we need at least 2, right? So the logic buffer is simply an arrowhead, this symbol right here, this triangle symbol, similar to the diode, similar to a NOT gate or an inverter gate. This is a logic buffer, isolation buffer. And so it comprises at least of 2 inverter circuits or 2 inverter gates. And that adds 4 transistors, so 2 plus 2. And so if you have a simple NOT gate and you wish to buffer it, 6 transistors, 10, 14, 18, depending on how much isolation or depending on your circuit parameters. Okay, if you have a 4-input NAND gate or a 4-input NOR gate, again, you're adding 4 transistors for each logic buffer that you wish to add. Okay, so it adds complexity to the device, and there are trade-offs. There are certain trade-offs. Okay. The first obvious trade-off is the more gates that you add, the longer it takes your signal to propagate through the system. Okay, so propagation delay is a big factor. So again, depends on your application, depends on your system. Propagation delay is the one big factor, one big consideration. Output resistance of these MOS chips is around, it's a few hundred ohms. Now, compared to the discrete resistances that you've been using, it doesn't seem as much, but it's still significant when it comes to like power consumption in microchips. Okay, so output resistance is a concern, and then the drive capability and the input capacitance. Input capacitance, of course, has to do with the capacitance that's due to the gate oxide. And again, remember in a previous class, we talked about how there's pros and cons to having both large as well as small value of capacitance. So it's kind of like a trade-off. Okay. So the same thing over here. The more gates we add, the more buffers we add, it affects the propagation delay, the output resistance, capacitance, and of course, how much current it can drive to the output. Okay. So on the left is unbuffered. Unbuffered gate. This is a buffered. What do we see? First and obvious is like the unbuffered ones have a slope. It's a gentle slope. This transition is not sharp, right? Here is quite a sharp transition, right? So there's a gentle slope transitioning from high to low and low to high, both ends of the transition. That means our noise margins must be smaller, right? Noise margin is the gap between what is considered as logic 0 and what is considered as logic 1. It's somewhere in the middle here. So that reduces our noise margins, right? If a noise signal arrives, if you're applying a system in a noisy environment or electrically noisy environment, then this would be a big concern. And so if you have a buffered gate, transition is quite sharp, noise margins can be increased. Okay. If you look, if you dive down into the spec sheets, we can see the pros and cons. So propagation delay, unbuffered gates. Obviously, since there are less number of gates, the signal propagates faster. Buffered gates takes longer. Look at the noise margins right here. Lower. The resistance fluctuates. And it's not consistent. The reason it's not consistent is because the states could get unpredictable. The more number of inputs you apply to these gates, meaning like a 3-input, 4-input, 5-input gate, the more unpredictable, the more the resistance will tend to go either down or up. Okay. All right, MOSFET symbols in digital circuits. So oftentimes you would be looking at some data sheets. You would have seen the enhancement mode MOSFETs and the depletion mode MOSFETs. Mostly we have studied the enhancement mode MOSFETs, right? They have the bar at the gate is divided into 3 parts, 3 pieces, right? So oftentimes it becomes very cluttery to analyze a circuit diagram. So we use simplified symbols like these, where the gate symbol is not portrayed as the typical enhancement mode MOSFET, right? You see, it's a straight line. It's not divided. Also, if you notice, there is a bubble. Typically in logic gates, and you would have studied, I'm assuming you've studied this in CP 133 digital design. What does the bubble indicate? Not inverter or zero or negative. So if it's on a gate, like a SR gate, SR latch, JK flip-flop, if you have a bubble, it means it's active low, meaning the signal must go to low or logic zero in order for it to become active. And we've seen, I think most of the logic gates we used in the lab, they were active high. So if you remember, the reset pin on the counters was connected to ground. The reason it's connected to ground is because it's an active high reset. If you apply a high signal, meaning plus 5 volts to the reset pin, then it resets the counter. So in order to not reset the counter, we connect it to ground. Anyway, so bubble indicates, here it just indicates the polarity of the actuating voltage, but bubble in general is when it's active low, which in this case would indicate a PMOS. And this would indicate an NMOS. Okay. So if we look at this, we look at this circuit here on the left, the logic inverter, 2 gates. We simply connect each other. Sorry, the gates are connected together, but you see the bubble here, and absence of bubble here means NMOS and PMOS. It's a simplified circuit diagram. Secondly, the bulk or the body or the substrate terminals are not shown. It's simply assumed that the connection is present, and it is present in a way that applies for the circuit. Especially if it's like a microchip, then it's already internally connected, then we don't have to even think about it. Okay, so the bulk or the body or the substrate terminal, B, is not shown. If you have a transmission gate, then we have our inverter here, VC, VC bar, and then we have a transmission gate here. Oh, yeah, bulk terminal not depicted. It's right here, which is marked as B. All right. Another special class of inverters or gates is the tri-state inverter. Sometimes we have undefined states with infinite output resistance, meaning output does not depend on the input at all, right? Undetermined. And so we add another enable button. We all use the enables in the logic ICs that we have in our labs, right? We had an enable pin. Until the enable pin is active, our device is not going to function. And so we can create a tri-state inverter like this one by connecting a transmission gate to the output. Okay. And so here we are applying, this is the inverter portion. And here's the enable. And we're using a transmission gate as a switch. In this case, it would be a digital switch. Okay. Transmission gate is simply taking the input, whatever the output of the inverter is, and sending it to the output. But the enable pin must be active. Okay, and that's how we introduce a third enable terminal in there. So again, going back to the example of the counter circuit or the counter chip that we used, there's an enable pin for both counters. As long as that enable pin is connected to high, then the counter functions. If it's connected to low, it's disabled. Enable pins in most logic gates are used to hold the output until the system is ready to accept it. Okay, so the inverter, as long as the power is being supplied, the inverter is going to hold the value, right? Whether it's 0 or whether it's 1, it's going to hold the value here. That's the output of the inverter. But until and unless the transmission gate is enabled, that switch doesn't activate, output doesn't reach. Okay, hence enable. Only when the enable pin is active is when the output reaches, and thus we have like a price state buffer. So it's an inverter. Can technically it has two inputs. It has the V in and it has the enable pin. Then there are some other circuits. There's positive edge detection. Wait, there was. I had got mixed up. Okay, positive edge detection circuits where we need to detect the edge of a up transition, right? Positive edge, negative edge. And so we delay the input going into the circuit. In this case, the circuit comprises of an AND gate. Okay, so there's a delay, and that delay can be accomplished simply by connecting multiple inverter gates, right? So there's a delay in going in there. Now the output of the AND gate is active only when both inputs are high, right? So there's a delay in the same input coming in. It can now take, let me draw this out like here. And this is B that is delayed due to these three gates, right? And now the output of the AND gate reflects whenever there's a positive going transition. AND gate is outputs are high only when both inputs are, I should stay away from high, both inputs are high. But output is 1 when both inputs are 1, right? 0, 0, 0, 1, 1, 0. Any of the inputs is 0, output is 0. So here we get a 0, 0, 0 because at any given point in time, this is 0 right here, and this is 0 right here. Okay. Only when both inputs are 1 do you have a 1. And so in this way, we take a single input, apply a small delay to it, feed it into an AND gate. Output of the AND gate is logic 1 only when both inputs are 1. So it's an inverted delayed output. Okay. And so the output of the AND gate is a positive edge detector. Does that make sense? Right. There are logic circuits are, it's very fascinating to me because you can create so many different kinds of circuits just by using any simple logic gates. All right, periodic steady state solution of an odd inverter loop. I wasn't planning on doing this, but since I already have it in here. So we have a propagation delay time for this inverter, TPD for B, TPD for C. Okay. Now, if you look through here, the outputs of every single gate will only be active once a signal propagates through, right? So the total propagation delay that ends up at the output, PD, is given by a low high and a high low transition. So right here, right here, right here. And now this one's already. Which one? Oh yeah, this is A, this is B, and this should be C. Yeah, there seems to be some error on this one. Okay, I think I need to revisit this slide later on. Either there's an error or I'm not understanding this correctly. There's something else on here. Right here. I'll have to take a look after class. Okay, ring oscillator. Ring oscillator is something we created in the lab. We had inverter gates. We connected them in series. The more gates we connect, the longer it takes for the signal to propagate. So when we take the output of the last one and feed it back as input to the first one, for an odd number of gates, we get a oscillation, right? Because it's switching constantly from 0 and 1, 0 and 1, 0 and 1. Output of the first one goes as input to the next. So if this output to begin with was 0, and the output here, actually, let's change it this way, 0, output here would be 1, this would be 0, and this turns to 1, which in turn goes to the input as 1, 0, 1, 0. And so the output of the last gate is oscillating between VDD and ground, 0 and 1, 0 and 1. And that gives us a oscillation. Now the oscillation, of course, is not going to be, it's not going to be a perfect sine wave. To simulate sort of a real life performance, we do have a capacitive capacitor output connected there. That represents kind of like the capacitance of the follow-on circuit with a load. Okay. Without the capacitor, you can simulate this, and when you simulate this, you'll see without the capacitor in there, it will be kind of only a square wave, but there might be some sort of small spikes or variations or distortions in the output signal. And then finally, we spoke about this in chapter 1 and 2, semiconductor fundamentals. In semiconductor fundamentals, we spoke about how we can take silicon wafers and create microchips, right? In the microchips, the word comes from micro or micron, which is 10 raised to minus 6 meters. Human hair is about the size of 50 to 75 microns, which is depicted here. And this was state of the art perhaps several years ago. And right now we are talking about feature sizes of 3 to 4 nanometers. So current state of the art is about 3 nanometers to 4 nanometers. And that's the current fabrication process. So it's incredibly detailed. There's only a handful of companies in the world can actually work on this fabrication technology. TSMC is one of the first ones. I think Samsung and Intel were trying to do something at this scale, but the yields were not as high. Anyway, so did I bring those wafers in the class to show? Okay, so students have an idea. So those wafers, those are microchips built here at Cal Poly on campus, built by students like you. Those feature sizes, I believe, were a few hundred microns, so quite big, quite large. Those are the capabilities that we have here. Even in research clean rooms, most of the feature sizes that we work with are on the order of like tens of microns. The smallest feature size I ever worked with was about 5 microns. Okay, so most academic clean rooms, research environments would be 5 microns. Specialized clean rooms in academia, where they do higher level of research, there they do get down to the nanometer scale. So there are researchers who do work with these small scales. There are students who work at these state-of-the-art level of feature sizes. Feature size on a chip is basically the smallest dimension of any feature in the circuit. And there could be millions of components and millions of features on there, but the feature size of the entire device is linked to the smallest one on the entire chip. So this one, the scale is shown as 100 nanometers. So this would be about 100 nanometer, 0.1 micron. 0.1 micron feature size. I've never worked on anything that small. Okay. The complexity can be appreciated by if you take your smartphone, the camera, go to its maximum zoom. If you go to the maximum zoom that your camera allows, and you try to focus on something and try to take a picture. And even if you rest your hand on a stable surface, you can appreciate how much that image, how difficult it is to capture that image. Okay. And so now when we're talking about something at the nanometer scale, if you're trying to imprint a pattern at the nanometer scale and you miss it by a few nanometers, your entire device is useless. Okay, because everything is built on a sandwich, like a kind of like a sandwich structure. So if you make an error somewhere in those like 18 to 20 layers, even if like all 19 of those are correct and one layer is off, the entire device is rendered useless. And so the skills or the technology that is required to build these kind of chips costs hundreds of billions of dollars. And there are only a few countries in the world that actually do that. And there's only one country specifically that actually does the lithography. Some of you may know the name of the company. Anyone? Take a wild guess. Which one? Well, that's a country, but company. Which company makes that lithographic machines? ASML. That's why everybody wants a piece of ASML. It's a Dutch company, which all the major corporations have a stake in that company, and they banned that company from exporting their machines, certain places. Anyway, so there's a lot of material that we could cover, but I think I want to call an end to the material, most of the material here. If anything, I might cover like a MOSFET amplifier or one small circuit on Monday. So instead of class, I might just have an open Q&A session. Students can get their concerns answered. Anything about homework, quizzes, I need to work on the solutions and post them. So Monday's class, we'll just have like an open session and bring your questions, and we'll get everything answered and review for the final. All right, and then we'll have one last quiz on Wednesday. And yeah, and that's about it. Yeah. Okay. All right. Well, you all have a good weekend, and I will see you all on Monday. Well, during the lab at least.